Okay, good evening. This is Professor David J. Delos Reyes. Okay, my topic for this session will be alternating current machines, and I am now on lesson number 24. We are now on lesson number 24. So, for those of you who are following my channel under the long video format discussion of AC machines, we are now on lesson number 24. Okay, let's proceed. For tonight, I will be discussing AC machines, lesson number 24, and the title of the topic is Copper Loss of Transformers. Actually, I have given you already the formulas on how to compute copper loss of a transformer. Even the test on how to determine the copper loss, I've discussed already the so-called short circuit test. But as an additional method on how to compute for the copper loss, okay, our textbooks place a formula there, but the derivation was not given, so I tried to derive it myself. So for tonight, I will be deriving the copper loss as a function of the output load quantity square. Okay, it was not given in the textbook, so I derived it myself. So let's try to derive the formula. Okay, let's try to bring out the derivation. For a copper loss is actually the resistance, the loss of the transformer due to the winding of the resistance, or the resistance of the windings. Sorry for that one, right? So in general, a resistance will dissipate heat, right? And the rate of dissipation is actually given by the equation. It should be the square of the current times the resistance. So meaning to say, if you are given a coil and current passes here, and there should be R, okay, whether we like it or not, this coil here will dissipate heat, and it will be in the form square of the current multiplied by R. Okay, we are given the resistance, current passing through it, so whether we like it or not, it will heat up, right? That's why circuits are very hot, right? And the rate of the dissipation of heat rating is actually given by the equation the square of the current multiplied by R. So as you can see it, the current is squared, right? So if you try, assuming a current is 1000, and you try to square that one multiplied by a small resistance 0.5, okay, this is still a very big number because you square this one. So actually, if we could minimize the resistance of the winding of the transformer, even though this is big, right? But if the resistance is small, the product of I square multiplied by R will still be small. So designers are actually using windings for transformers with the so-called a perfect resistance thing. It should be pure copper, something like that. If it's a combination of a copper and aluminum, that's a different story, because the specific resistivity of aluminum and copper are actually different. Okay, I will try to erase this one. Okay, that's the story of the product I square multiplied by R. It's the rate of dissipation of heat. Okay, whether we like it or not, okay, as current passes through the winding, it will heat up. That's why transformers are actually a very hot equipment. Okay, they got cooling fins, they got cooling tubes, air is even blown to them to dissipate the heat, and the rate of dissipation is actually given by this equation here, I square multiplied by R. Because if the current is very big, whether we like it or not, that power will be very big, and it's very hot. Okay, I will try to erase this one. So I will now try to derive the equation which will give us the copper loss in terms of the power of the load. It was given like this in the textbook, right? Capital letter P with the subscript copper, meaning the copper losses, equal to certain constant K multiplied by the quantity volt ampere output quantity square, and the unit of this is in watts. Okay, we'll try to derive this one, why copper loss is directly proportional to the square of the volt ampere output. Volt ampere is actually the apparent power, S, quantity square. It is the total power, okay, drawn from the utility line going to our houses or business entities, right? It is this. So as you can see it, if this is big, the copper loss should be big because this is raised to the second power. Okay, let's try to derive this one. Using the equation P with the subscript copper, meaning copper loss is actually I square multiplied by R. Okay, using the secondary values. Actually, we are given here a transformer, right? If we use the secondary values, the values on the secondary, okay? So using secondary values, capital letter P with the subscript copper, meaning the copper losses, should be equal to, if we try to use the secondary values, all the subscripts should refer to S, meaning secondary values, right? So this current now, I will place a subscript. This should be capital letter I with the subscript S raised to the second power multiplied by. If we are using the secondary values, the resistance that we will be using will be the equivalent resistance referred to the secondary. So this should be R with the subscript E, again with the subscript S, meaning subscript E is equivalent, subscript S is actually referred to the secondary. So RES is actually the equivalent resistance referred to the secondary. Okay? That will be equation number 1. Okay? Let's try to define what is volt ampere. Volt ampere. Volt ampere is the product of voltage and current, right? So on the left hand side, if I will place B times A with the subscript S, S refers to secondary, this should be equal to, you see the subscripts, it's all S, right? So volt ampere on the secondary should be equal to the induced voltage on the secondary times the current on the secondary. And if we try to compute for this, okay, it will be volt ampere on the secondary divided by S. So IS here, meaning the current on the secondary side, will be the volt ampere on the secondary side over the induced voltage on the secondary side. Right? In here, I just place the subscript. Actually, this one is this one. Right? So if we try to get this value here, we put it here. Okay? We'll go back to equation number 1. Capital letter P with the subscript copper. Hold on. My camera is still fine. Capital letter P with the subscript, meaning copper losses, will be equal to the secondary current square. But secondary current square in terms of apparent power and induced voltage is this one. So it should be volt ampere on the secondary over induced voltage on the secondary quantity square. This is to the second power. Right? Times the equivalent resistance on the secondary. Right? If we try to square this one, the first one will be volt ampere on the secondary quantity square, okay, times RE to the secondary. There is an ES square at the bottom, right? But I put it under the RES. Okay, so this should be E sub S quantity square. And we will try to represent this one as simply K. Okay? For any transformer, the equivalent resistance on the secondary is constant. The induced voltage on the secondary is also constant. So a constant over a constant will still be a constant. So we will represent this ratio here as simply K. Okay? So what will come out now? Capital letter P with the subscript copper, meaning copper losses, should be equal to K. We replace this by K. So this is K times a volt ampere with subscript S quantity squared. Right? But if we try to look at the secondary side, the output on the secondary side is actually the voltage output of the transformer. Okay? Instead of placing the subscript S, we will just place the subscript output. Right? So, copper losses now, meaning capital letter P with the subscript copper, meaning the copper losses, should be equal to K times the volt ampere output quantity squared. And the unit of this is watts. Okay? So, from our textbook, this was given, but it was not derived like this. So, I brought out the derivation. So, what comes out is the one on our textbook. That is the copper loss is equal to certain constant K times the volt ampere output quantity squared, and the unit of this is watts. Oh, you can use this one as kVA, it doesn't matter, right? Or volt ampere. Because in the computation of the value of K, if this is kVA, we can compute for K. But even though this is only volt ampere, you can still compute for K because you're referring to the same transformer, right? Okay. So what's the importance of this formula here? This is actually the fourth formula on how to compute for the copper loss of a transformer. Because actually we are given three formulas. The first formula, the copper loss, is actually the copper loss of the primary plus the copper loss of the secondary is actually the total copper loss. By using equivalent values, copper loss is also the square of the current of the secondary times the equivalent resistance referred to secondary if we are using secondary values. Okay? Third one, copper loss will also be equal to the square of the current of the primary times the equivalent resistance with the subscript primary if we are using primary values. Okay? So actually there are four formulas on how to compute for the copper loss of any transformer. So any of them will do. Okay? If you are given the voltage output and you know the value of K, you could compute for the copper loss. If you know the primary current, you know the primary resistance, you know the secondary current, you know the secondary resistance, take the sum and that will still be the copper loss. If you know the equivalent resistance referred to the secondary, okay, secondary, you multiply by the square of the secondary current, that will still be the copper loss. Last one, if you know the equivalent resistance referred to the primary, you multiply that to the square of the primary current, okay, that will still be the copper loss. Okay, this is quantity square, this quantity square. But the one that was derived tonight is actually K times the volt ampere output quantity squared. This key here should be known. Because without knowing the value of K, we cannot compute for the copper loss even though the voltage output is given. So there should be an initial condition, okay, in which the copper loss is given. So the problem is asking for any copper loss at any percent of load, we could compute. Okay, so this one is actually the copper loss for taking the copper loss at any load condition. 1/4 load, 3/4 load, 50% load, or at full load. This will be the equation. Okay, that's it, guys. That's copper loss. This is Professor David J. Delos Reyes. Good evening from Los Angeles.